For the part 2, we have here the Intel 4004, the genesis of the CPUs, because in March 1971, it is the commercial launch of the Intel 4004 CPU, which set the stage for a new era, composed of then incredible 2300 transistors. It was initially custom chip for a calculator. Its release to the public was heralded by prophetic irony, announcing a new era in integrated electronics. It was a 4-bit CPU, could execute up to 92,500 instructions per second, consumed just 1 watt, and cost about $5 to produce. Compare this to ENIAC, built 25 years earlier, that weighed 27 tons, consumes 108 kilowatts, and costs of millions. The 4004 laid the groundwork, providing the immense computing power that could be miniaturized onto a single affordable silicon chip. Next is the CPU evolution. The evolution of these CPUs was rapid. The 8008 added interrupts and indirect addressing. The 8080 at 3.1 megahertz was considered the first reusable microprocessor, but the watershed moment came on June 8, 1978, with the Intel 8086. This was a full 16-bit CPU designed with a software-centric ethos. It introduced the complex segmented memory model to access 1 MB of memory, and crucially, it established the then or the x86 architecture. Its most enduring characteristics was a commitment to backward compatibility. This decision, allowing old software to run on new chips, created an unbreakable ecosystem that would define the PC market. Its variant, 8088, was chosen for the IBM PC in 1981, cementing the fate of both Intel and Microsoft. Next is the interrupt handling concept, or the responsiveness, the interrupts, and indirect addressing. So as CPUs needed to interact with the dynamic world, two key features emerged. Interrupts allows hardware signals, a keystroke, a timer tick, to immediately pause the CPU, force it to run a small high priority service routine, and then seamlessly return its back state. This is the bedrock of responsive real-time interaction, in while indirect addressing is a software powerhouse. Instead of instruction containing the data's address, it contains a pointer to that address. This enables powerful data structures like vector tables, letting a program use simple index number like 3 to look up address of a complex piece of data like sentence 3 in a list. Both features move computing from simple calculation to complex dynamic interaction. Next is the early CPU evolution, Intel 8086 segmented memory. So to access 1 MB of memory data with a 16-bit architecture, the 8086 employed a segmented memory model. Memory was divided into 64 KB chunks called segments, one for decode, one for data, one for stack. An address was specified by a segment register and an offset. This was a crude form of virtual memory. It gave programs the illusion of a dedicated 16-bit address space, while the hardware mapped it to the physical RAM. While cumbersome and error-prone for programmers, it offered pseudo sandbox and was convenient for the smaller programs of the era. If you ever run a DOS.com file, you were loading a binary dump meant to fit entirely into one of these 64 KB segments. Sorry. So, next, multitasking visualization. The 1980 software boom demanded a fundamental shift. Running multiple programs or processors concurrently in a single task system, a program waiting for I/O wastes, CPU cycles, and crash takes down everything. So multitasking solves this by having the operating system act as a conductor, rapidly switching CPU focus. This creates the illusion of parallelism. Early systems use cooperative multitasking, relying on programs to politely yield control. A fragile system prone to freezes. The modern solution is preemptive multitasking, where the OS allocates fixed time slices. This isolates processes, guarantees system responsiveness, and allows the CPU to work on another task while one waits for a slow disk or network, dramatically improving efficiency and stability. Next is the MMU, Memory Management Unit, the expanding memory or the virtual memory and paging. The MMU enables a powerful illusion, the virtual memory. This technique allows a system to use more memory than it physically has by using this storage as a slow extension of RAM. The MMU breaks memory into fixed size pages. Active pages reside in the fast RAM. Inactive pages can be swapped out to disk. When a program accesses a swapped out page, a page fault occurs. The OS then fetches it from disk and execution resumes. This is seamless to the program while disk access is slow. This swapping allows massive applications to run and enables the multitasking with many programs loaded simultaneously. It's a clever trade-off between cost, capacity, and speed that is central to modern operating systems. Now, we have the architectural duel between CSICI SC versus the RISC. In 1980s, crystallized two competing CPU design philosophies. Intel's x86 was quintessential CISC, or complex instruction set computer. It featured a large, robust instruction set where single instructions could do complex work like multiply, re- reduce or reducing program size and memory accesses, a key advantage when memory was low and expensive, while the rival RISC philosophy, reduced instruction set computer, seen in the Motorola 68K and others, use a small simple instruction set. Each instruction did one thing typically in one clock cycle, making pipelining easier and enabling a higher clock speeds. So, and the trade-off, RISC compare programs rather needed more but simpler instructions. Today, this slide is blurred. Modern x86 chips use RISC like cores inside, translating complex CISC instructions into streams of simple micro-ops for execution. Now, the Motorola 68K versus the Intel x86. This duel was personified by the Motorola 68K and Intel x86. The 68K was the programmer's darling, or the clean orthogonal with a flat 32-bit memory model and simple, powerful instructions. It powered the original Macintosh, Amiga, and early workstations. Its design emphasized elegance and ease of use. The x86 lineage, in contrast, was a pragmatic accumulation of complexity burdened by its segmented memory and irregular instructions, all in the name of backward compatibility. While the 68K offered superior engineering model, 8 x86 strategic alliance with the IBM PC and Microsoft DOS created the unstoppable commercial ecosystem. This history shows that in technology, market forces and strategic partnerships can sometimes outweigh pure technical merit. Next is the protected mode architecture 8286. The Intel 8286 marked a bold attempt to bring mainframe grade stability to PC with protected mode. Protected mode. This was a revolutionary new operational state that introduced hardware enforced memory protection and four level of privilege system. Memory was managed as protected segments described by descriptors in tables. These descriptors enforced boundaries and access rights. If a program violated these rules, the CPU triggered a fault. The isolated programs and OS kernel, preventing crashes from bringing down the whole system. While groundbreaking, the 286's protected mode was flawed. It couldn't switch back to the real mode without a reset, hindering adoption. Bill Gates famously called it brain dead, but its concept would be perfected in the next generation. Next is the instruction pipelining. To overcome the underutilization of the fetch, decode, execute cycle, engineers developed instruction pipelining. Imagine a CPU assembly line. While one instruction is being executed, the next is being decoded, and the one after that is being fetched. This overlap dramatically increases throughput. However, it introduces hazards. A data hazard occurs if an instruction needs data still being calculated by a prior instruction in the pipeline. A control hazard happens on a branch where the CPU might fetch the wrong instruction path. Sophisticated solutions evolved to manage this. Operand forwarding to shortcut data branch prediction to guess the right path, and out of order execution to keep the pipeline full. Pipelining transforms CPU design from a sequential processor to a parallel orchestration problem. Next is the CPU cache hierarchy. A CPU clock speeds far outdated RAM. Accessing main memory became crippling bottleneck. The solution was caching, adding small amounts of very fast static RAM or SRAM directly on the CPU die. Caches exploit locality. Programs tend to reuse recent data and access nearby data. Modern CPUs use a hierarchy, tiny ultra-fast L1 cache, and a larger L2 cache per core, and a large shared L3 cache. When the CPU needs data, it checks L1, then L2, then L3. A cache hit is fast. A cache miss forces a slow fetch from RAM. Cache design involves complex trade-offs in mapping, replacement policies like LRU, and write policies, write through versus write back, and all engineered to achieve the highest possible hit rate and hide them from the memory wall. Now, for the conclusion, the unending evolution. The evolution of the CPU is a masterclass in overcoming constraints through ingenuity. We've journeyed from the simple deterministic 4-bit word of the 4004 to the complex, speculative, and parallelized realm of modern processors. We saw how the need for software ecosystems cemented the x86 architecture, how the demand for stability reverted the productive mode and the MMU, and how the pursuit of efficiency led to the pipelining and deep cache hierarchies. This story isn't about just transistors and clock speeds. It's about the feedback loop, hardware and software, where each breakthrough enables new ambitions in the other. Understanding these foundations allows us to appreciate the incredible engineering and that the quietly powers every click, tap, and connection in our digital world. That's all. Thank you.